In this video, we're going to talk about the units for the equilibrium constant K. So up to now, we've just sort of been leaving off the units. And the question is, should we be doing it or shouldn't we be doing it? So let's take an equilibrium. So 2 molecules of A in equilibrium with 3 molecules of B. And at equilibrium, we measure the concentrations of A and B, and maybe the concentration of A is 0.1 molar, and the concentration of B is 0.2 molar. So we can form the equilibrium constant. So we can go ahead and we can say K, and since we're dealing with concentrations, it'll be Kc is the concentration of B cubed over the concentration of A squared. Remember, we get the coefficients become powers in the equilibrium constant expression. So we take 0.2 molar and we cube it, and we take 0.1 molar and we square it. And if we calculate that, we get 0.80. Now, what are the units? So at first glance, it looks like the unit should be moles per liter because we've got moles per liter cubed on the top and squared on the bottom. So we just landed up with just a single moles per liter. But it turns out that for all these equilibrium constants, you ignore the units. You don't write them down. They are actually unitless. That is to say, they are pure numbers. And you might look at this and say, that's not right. That can't be the case. How do you get rid of those units? And it turns out there's two ways to approach this. One, you can just say, we throw them away and ignore them, and that's just the definition, end of story. Or two, you can go down this little rabbit hole with me, and I can tell you why those units are not there. So it's up to you. If you want to, you can completely skip this next part and just say, I throw away all the units, whether it's Kc or Kp, I throw them away and write down a pure number. Or you can learn why. So up to you. Great, I'm glad you decided to stick around. So here's the real story. So let me go to a completely new slide and show you what's really going on here. So what's really going on here is when we write an equilibrium like 2A in equilibrium with 3B, we said earlier the equilibrium constant Kc is equal to the concentration of B cubed over A squared. But that's not actually the case. It is actually equal to the activity of B all cubed divided by the activity of A all squared. So A is the activity. Now, of course, that doesn't really help you, right? So what is an activity? An activity, we can go ahead and say it's roughly equal to the concentration of something divided by the standard state concentration, which in this course will always be 1 mole per liter. So we can go ahead and we can replace our equilibrium constant expression with the activity. So the activity of B, that's just the molar concentration of B divided by 1 mole per liter. And we're going to go ahead and cube that. And we're going to do the same thing for the bottom. The activity of A is the concentration of A divided by 1 mole per liter. And we're going to go ahead and square that. And so, of course, now you can see that the units end up canceling out because whenever you divide something by 1, it doesn't change the number. But if you divide by 1 molar, it essentially cancels out the molarity and leaves you with just a number. And so we saw in the last problem that this comes out to be 0.80, and it doesn't have any units whatsoever. Now, if you're dealing with gases, so if you're dealing with Kp, and remember we could write the Kp expression, it would be the partial pressure of B cubed over the partial pressure of A squared. In reality, it's the activity of B cubed divided by the activity of A squared. And actually, when we're dealing with gases, the activity of a gas is equal to the partial pressure of the gas divided by the standard pressure of a gas, which again, we take to be 1 atmosphere. Okay. And so again, if we're dividing by 1, we're not changing the number, but the units are essentially canceled out, and so we just have pure numbers. So now you know the secret. Now you know why equilibrium constants do not have units. Wasn't that fun?